Okay, welcome back to a new physics tutorial. In this video I would like to explain a method which is called Newton's method. This is actually a method in order to calculate the root of a function numerically. And you can, normally you are interested in analytic solutions of equations, but in this case, maybe sometimes it's not possible to find an analytic solution, or in some cases it's also too difficult to get it. So then in this case you use numerical methods. And in Newton's method has the advantage it's easy to use. You only have to calculate the derivative of a function, of the function that from which you want to find the root actually. And then you can use a recursive formula to reiterate the result that you get. And the more iterations iterations you make, the better the result will be at the end, the closer it will be to the analytic solution that you get. And maybe you use this method also much more often than you think, because many computer algebra systems are using this method. When you want to calculate the root of a function numerically, then there are several methods available, and I usually like Newton's method because, as I said, it's easy, and computer algebra systems are also using that. But of course there are also other possibilities which I maybe will introduce in one of the other videos. But for the time being we will use this one. I will start explaining now with a small sketch why this method works and what is the idea behind it. Then after that I will make a very short mathematical derivation, how to reach to the formula that we want to use, and then at the end I will also make a small example to explain everything in a more detailed way, and then you will also get used of that, how to use this formula that we get out in the end for your own purposes. So the first thing which I would like to do, as I said, I would like to show you why this method works with the help of a plot. So what we will do now, I hope I can draw this in a good way. We will draw a coordinate system here, x and y, and then we draw any arbitrary function here. That could be, for example, looking like that. And then you see this has two roots, and we are now interested in this one here. So what we do, we choose an initial value here. Maybe we can use another color for that, which could be, for example, here, and this is called x0. And then of course we have also here a function value f of x0, which is not so much interesting for us, but it's we can define that, of course. And then I would like to draw a tangent through that point here, which we have defined. So I will also try that. Maybe like this it will look. And then you see here, this tangent is intersecting the x-axis. And then maybe I use again another color. And this we actually call now, or this position we call x1. And again, we can also calculate the position, the function value here of x1, and this would be f of x1. And then we can draw another tangent through this point here. Maybe this will look something like that. And then we have another value here, x2. And then we can do the same again and again and again, until we finally see that the more often we do that, the closer the intersection of the tangents with the x-axis, the closer it gets to the root of this function. So if you do it an infinite amount of time, you will get the exact value for that. And this is, as you can see, very powerful method to do that. The only thing which we need from this function, as I said before, is the derivative, because when we want to draw tangents on a graph intersecting the graph in one point, then we actually need the derivative to calculate the slope at this point. And this is already everything what we need to know in order to really calculate or derive the formula that we want to use. Maybe you have seen that also before. We will start easy with the so-called tangent equation, which is very simple. It's actually just a straight line, mx plus b. So this is, I think you have seen this maybe multiple times already. And of course, what we can say also is that the tangent at this position x0, as I said before, is equal to the function value at x0. So we can write f of x0 is t of x0. And if we insert this x0 here in our tangent function, then we have mx0 plus b. And also what we can do here, because we know already, as I said, the slope is equal to the derivative of f with respect to x at the position x0, we can directly write here f prime of x0 times x0 plus b. Okay, and yeah, this is already the ansatz that we have. What we can do now here in the next step is actually solving this for b. Yeah, we want this parameter here, b. And we can do this also easily. I mean, this is when you do that here, I mean, you solve this function here, put everything here, what is written here onto this side. Yeah, so then at the end we get b equals f of x0 minus f prime of x0 times x0. Yeah, this is really not so difficult. And now we can use this sphere and insert into our tangent function, which we have f of x. So what we do now, maybe we can use green. So what we have here is our b parameter, and we want to insert this here. Yeah? So this we want to replace actually. Yeah? So when we do that, then we get at the end for our t of x, this is then f prime of x0 times x plus f of x0 minus f of x0 times x0. Yeah, okay, maybe I can try to delete that because it looks a little bit ugly. So there should be a minus sign. So now what we can do, we have now our tangent equation here with respect to the derivative of f and f itself. But now we also want to calculate, as I have explained before, the intersection with the x-axis. Yeah? So this point we will call x1, as I said, or this position. So we calculate now t of x1. And this should be then, of course, equal to f prime of x0, x1, plus f of x0 minus f of x0, x0. And yeah, and then, of course, as I said, this has to be equal to 0, yeah, the intersection with the x-axis. So now in the next step, what we can do is dividing this whole equation by f prime of x0. And this we do in order to isolate this x1 here. Because this is what we want to get at the end. Yeah, and when we do this, so we have to divide this here by f prime of x0, as I said. So now we can write here x1 plus f of x0 divided by f prime of x0 minus x0, and this has to be equal to 0. Yeah? So now the only thing which we have to do, and for this maybe I will make a new page, is solving for x1. As I said, this we want to isolate. So we get here x1 equal x0 minus f of x0 divided by f prime of x0. Yeah, and this is what we want to get. So we, as I said, we have to define initial value here, x0. Then we have to insert this initial value into f of x and f prime of x. And then we get here our new value x1, and then x1 we have to insert back here into our equation. Then x0 changes to x1. Here this will give a new value x2, and so on and so on. Then you have to do this iteratively several times. So this is then finally leading to this formula, which is called Newton's method. And we can write this in the following way. We write here xn plus 1, this is this part here, equals to xn minus f of xn divided by f prime of xn. And now we have our recursive formula, and this we can actually now highlight in red, because this is the important thing that we need. And in order to get familiar with this, we can really make an example now, and I have already tried this for a certain function. Let's try how it is. Example. So I've just taken this function here, f of x equals x square minus 10x plus 5. Of course, you can also try this with any other function. Maybe it should, in this case, it's easy because it's also a polynomial. You can also try something completely different. And if it's not too crazy, then it should actually give you a good result if you choose x0 correctly. So in this case, as I said, we need the derivative, so we can already calculate f prime of x. And this would give a 2x, and this would give a 10 minus 10, and this 5 vanishes because it's just a constant. Now we also have to, of course, define initial value, and this has to be already close to the root. Of course, I have checked that before, and I found out that if we use x0 equal to 1, then we are already in a good shape. So now what we have to do, we have to insert this into our Newton's function. So we get here our Newton's method formula, and we get here x1 equals 1 minus f of 1 divided by f of 1. This is our x0, and when you do that, you get a value of 0.5. And you will see later that this is very close already to the root of the function. So now in the next step, what we can do is calculate, of course, x2. And then we have to insert this value here back into our formula. This is f of 0.5 divided by f prime of 0.5. And when you do this, you get 0.527778. I think it's just periodic 7. And then in the next step, you have to insert this back into this formula and reiterate this again and again and again. And I have done this already up to 10, and you can use Excel for that. That is very simple. You can just insert x0 in one column, and then you can drag this formula down and get then as many iterations as you want until your memory is full. And I have done this up till x10, and so the 10th iteration, and then I get here a value of 0.52786405. And this is already very close to x2, so you will see that it converges quite quick. After a few iterations, you have already a result which is very close to the analytic value. And even the first one is not so far away. So if you want to have a very rough estimation where the root might be, then maybe even 1 or 2 iterations should be sufficient. But as I said, it works quite well. Most of the functions you can do that, as long as you can calculate the derivative and x0 is not too far away. You have to play around. Maybe you can plot the function before with a calculator. So what you can do, you can calculate it for a certain amount of values, then for some other values, and when you see that for the first values that you calculate, the result is the function value is negative, and for the other one it's positive, it means the 0 value, the root, must be in between that, and then you have already a good approximation. If you really don't know where to put this, then you can maybe use just create a table, and then you can calculate this for several numbers, and at the end you will see what comes out from that. Okay, so I hope that this video was beneficial and you learned something for your studies and also for calculating numerical solutions of roots of functions. And if you liked the video, then I hope that you click on the like button, that you write into the comment section if you have any further question, or if you want me to continue with that. Then if you want to see further videos, please also subscribe my channel if you have not done so far, and hopefully see you soon for a new video.